Hello. In today's lecture, we are going to look at how to design an ultra wideband antenna. By the way, I'm Dr. A. Sriram, working as an assistant professor in the Department of ECE, SRM Institute of Science and Technology, Katangaluttu, Tamil Nadu, India. And before we get into this designing of an UWB antenna, I mean ultra wideband antenna, let us see what is meant by ultra wideband. So ultra wideband, it is nothing but it is a frequency range which is lying between 3.1 gigahertz to 10.6 gigahertz that is being defined by this Federal Communications Commission. And this frequency is being widely used for different types of application because that has that very important characteristics that which can have it transmit the data at very high data rates over the short distances with a minimal power consumptions. So there are several frequency band that has been used. You look at this ultra wideband, which is ranging from 3.1 to 10.6 gigahertz, in which you have several frequency band and several applications that may lie on. So we can make use of this ultra wideband antenna for the different kind of application to have a data transfer. What are the significance of ultra wideband technology? Because it has a very high data rates to handle different types of communication with high capacity, and which has a very low power consumption. As I said, when you want to integrate such an antenna with a battery power source, the battery cannot be drained very fast. So ultra wideband antenna is had that very specific character, the low power consumption and then low power spectral density, and which also mainly used for this MIMO communication, which has a very high multipath immunity and fine range resolution capabilities, which is being used for different types of application. There are a few important applications that I have listed in this slide. One is that Internet of Things, and next one is automotive communication, which can be used for this healthcare, and which also mainly used for this defense and many more like wearable application. Also, we may go for using this ultra wideband antenna. So looking at these applications of this ultra wideband antenna, one of the important applications is that short range communication. So which is used for this high data speed transfer communication, especially when you go for streaming that HD movies, and you want to have transfer of data between the devices at high data rates, and especially by using this wireless USB, and which also has a very low latency communication, because when you want to play a game or with any other data communication, that should have a very low latency, especially for this VR or AR communication system. You have that peripheral devices which being fixed in your body. When you move the devices accordingly, the same thing has to be reflected on the screen also. So we need to have very faster data transmission with a very low latency communications. And next one of the application is that precise location positioning. And we may look at it this indoor navigation, where this UWB is being extensively used in that the indoor environments where the GPS signals are unreliable, such as we may look at the warehouses, airports, and malls. The next one is the asset tracking, which can track that. You may look at in the industry sites. People may want to count the number of equipments or the tools are inventory like, and we may also look at these healthcare centers. And next one is the real-time location systems for monitoring the employees and the patient in facilities like hospital and means. And especially we may look at some nuclear plants where the employees may work inside the nuclear plants, need to have the health monitoring, where we can have this ultra wideband antenna frequency ranges. We may go for using it. And next, very important one of the application is that automotive communications, where we may look at the several features are there, where few I have listed on this slide. You may look at the keyless entry systems, where the UWB enables secure and precise communication between the car and its a key fob. And next one is a parking assistance, and it assists a proximity, that the decision and the collision avoidance. And vehicle to everything, you like to have the ultra wideband can contribute the communication between the vehicles and the pedestrians, and as well as in that can also be used for that advanced driver assistance systems. And next one is the military and defense, where the radar system, where the UWB is used for penetrating through walls, and the ground for surveillance and that detection. And communication system, you like to have the secure and high-speed communication in the tactical for the tactical operations, and search and rescue, where the landslides are there, where you need to locate that location accurately in the disaster recovery efforts. And next one is the consumer electronics. As I said, you may look at this augmented reality, AR, VR, virtual reality. This UWB enables the precise positioning and enhancing immersive experiences as it have very high data rate speed and wide bandwidth. And besides, it also has this low latency. And especially for these wearables, also can be used for this UWB application for fitness tracking and health monitoring with a low power consumption. Because as when you go for this wearable communication, when you go for an antenna fixing on your body, not in body, it is on body, then the power should not affect that cells of our human tissues. So we should have a low power consumption, this ultra wideband antenna, which has that one of the very feature that low power consumption. Next one is the smart home and the IoT devices, and which can be used for interconnecting the multiple devices at different locations inside our house, which can have a coordination between them. And next one is the gesture recognition, because the UWB sensors can detect the movement and the gesture, which enables a touchless control of the smart devices. And next one is the secure access. When you look at the security of it, the UWB provides enhanced security for smart locks and the access the control systems. So we have seen a lot of applications where this UWB technology that can be used for. So one of the major advantages of this UWB technology is the low power consumption. Next one is that we can have the precision, because the UWB offers the location accuracy within a very few centimeters. And next one is the minimal interferences, because that operates across a wide spectrum, and that can have the reduction in the signal congestion. Moreover, that we have seen all the things and the side of the theory of ultra wideband frequencies and technology where it's being used. Now we look into the next part of this video is that designing an ultra wideband antenna. So there are some important matrices that need to be considered for designing an UWB antenna. One is first one is that what are the requirements for designing an UWB antennas. Next one is what are the design challenges we are going to face while we design an antenna. Next one is what is the design parameters we have to give more important to it. Now, looking at the requirements for designing a double antenna, we need to have an antenna that should provide a large impedance bandwidth that is covering from 3.1 to 10.6 gigahertz, and that also should have a high radiation efficiency, because that need to minimize the energy losses. Then compact size for the integration into small devices. When you go for wearable devices or integrating on that automotive communication, the antenna should be very compact in size so that that can be fixed anywhere else. And now next one is the stable and reduction radiation patterns that should have a reliable communications based on the application, because some application requires the directional radiation pattern, some application requires omnidirectional, some application requires the bidirectional. So based on the application wise, we should have a stable radiation pattern which can ensure the reliable communication. And it also should have the requirement of low group delay, because that it is need to minimize the signal destruction. Now, what are the design challenges we are going to face? The first one is that we are going to design an antenna that need to cover a very large impedance bandwidth, that is 3.1 to 10.6 gigahertz. So our antenna should provide a good impedance matching over the large impedance bandwidth. Next one is the compact size and the performance. So balancing the minimization of this size of an antenna and the whose performance should not go down. So that is also very important. So the efficiency should be high by balancing the minimization. Next one is the interference management, because as you know, the frequencies which is covering from 3.1 to 10.6 gigahertz, which can come with the multiple bands within that. So we need to have the avoidance overlapping with the existing narrowband systems, and radiation efficiency, which also should overcome the losses due to the compact designs. Now, what are the design parameters that we need to look at to validate our design of UWB antenna? First one is a return loss, but because that reflects the impedance matching between that frequency ranges of 3.1 to 10.6 gigahertz. And next one is that voltage standing wave ratio, that is VSWR, that should lie between less than 2. And the bandwidth need to be measured. That must be less than minus 10 dB, and the gain and efficiency are the very important matrices for that performance. Then radiation pattern, the what type of application, what kind of radiation pattern we require, where we require this omnidirection pattern or the directional pattern, which can be differing based on the application side. So still now we have looked at what are the application, where is being used, what are the requirements, what are the what are characteristics of UWB antennas, all those things we have seen. Now let us see how to design ultra wideband antenna using a CST tool. So for this, I have my scholars. They will explain how to design a UWB antenna. For that, they have referred one base paper. From that, they will replica the same design what is available in the paper to our CST tool. So it may help you for learning how to design an antenna using CST tool for these ultra wideband applications.
Hello everyone. Now we are going to design an ultra-wideband rectangular patch microstrip antenna, which is an ultra-wideband antenna where the antenna is radiating from 3 GHz to 10.39 GHz frequency. And here, this is the proposed design which we are going to replicate now in the CST software. And here we can see all the dimensions are mentioned here, and every details are mentioned here about the antenna. So now Harshni will start the designing process. Harshni.
Thank you. As we open the software and we'll get the preface like this, we have to select the project template and sorry, and we have to select the microwaves and RF opticals. As we are designing the antennas, we have to select the antennas and we have to proceed for the next step. And we are going to design the patch antenna, so we have to select the planar or patch and stuff, and we have to proceed the next step. And make sure that all the dimensions should be in units, like millimeter units. And we have to select the next step. And here they have asked to mention the minimum and maximum frequencies. So we can give here also, and also, or else we can give in further steps. It's not an issue, and we have to proceed for the next step. Yeah. Before designing an antenna, actually antenna contains like have three parts. So, patch, substrate, and ground plane. So here the blue color one is a patch. This one is the first layer of the antenna, and the middle layer of the antenna is the substrate, and the last layer, like below layer, is the ground plane. So here they have given the partial ground plane. So we have to design, like we have to create the substrate first. So for that, we have to go for the modeling and we have to select the brick here and we have to press the escape button.
Harshni, sorry for interruption. Before going for the designing ones, could you please show the obtained results?
Yeah.
Like we have already designed, no?
So this is the antenna we have already designed and we have we got the results for this, and these are the appropriate results which we got.
Here we can see the antenna is resonating, radiating from 3 giga, almost 2.9 to 10.39 gigahertz frequency. Harshni,
Charan,
no problem. Go for designing.
okay, yeah. So initially we have to create the substrate here. So the name I'm giving is substrate. So, so here we can give the direct values and or else we can give the variables. So I'm giving the variables here because it is easy to change the, if you want to change the any values of the part.
Harshni, show the example, like what is the use of giving the variables?
Yeah, yeah,
Show the demo in the previous design.
yeah. As you can see, I have given the all the variables here. See, if I want to change the any, for example, uh, This is the substrate length. Length of the substrate is 30 mm. So I have given the name as
Uh,
LS. See, I have given the variable here, and for the variable, I have allotted the constant here. If I want to change the length of the substrate, I can change the value here directly. Like if I want to change it to 20 mm, I have I can give the value, and I have to press the enter. Okay, and F7. Here the substrate length have been decreased. As you can see, here it has changed to 20 mm. Again, I want to change it to 30. 30, enter, F7. It became normal.
so whenever we are giving the variables instead of the direct values, it is very easy and convenient process for the alteration purpose in order to obtain many better results.
So it
So
is,
that's why we are going for the variable method.
yeah,
If we are giving the direct values, it is very difficult to alter the substrate length, not only substrate or any part of the antenna.
either it may be slot or length or width of the antenna. So it is very tough to change the dimensions of the antenna. So if we give the variables to the uh, like substrate or anything, so it is easy to change here so that we can observe the changes here. Can I proceed, Charan?
Yes, Arshil.
Yeah. So here I'm going to give the variables here. So for x-axis, it is the width. So
Yeah,
I'm,
Harshil, sorry for interruption.
yeah,
Whenever we are going for the dimensions, we will start from the minus to plus. So then only it will cover the whole part of the antenna. So here we are starting from the minus x-axis is minimum and to the maximum of plus x-axis. So Harshini, give the value like minus ws by 2.
yeah, yeah. So here I'm giving the x minimum as minus ws by 2. That is width of the substrate divided by 2. I'm not giving the ws here. Ws divided by 2. Here, ws divided by 2. And y minimum is the length. Y-axis is the length. So I'm giving ls divided by 2, like length of the substrate divided by 2. We can allot the any of the variables, not only ws or ls. We can give the a by 2 or b by 2, c by 2, anything. So
Harshini, on uh, we will now I will explain that part like how why we are taking from minus x-axis to plus x-axis and then minus y-axis to plus y-axis. Uh, we can see some grids over there. So the center point is 0, and if we are going for the left side, which is in minus x-axis, and we are going for right side, which is plus x-axis, and same in the y-axis also it is same. So the antenna, while we are designing, the minimum will start from the minus x-axis, and the maximum it will go up to the plus x-axis. So that's why we are taking from minus to maximum plus in the same in the y-axis also. And the z-axis is thickness. Harshit, want to show the bottom part.
yeah.
Yeah, this is the z-axis. Yeah, Harshit, you can go for the dimensions.
Yeah. So for the Z minimum to Z max, for the substrate, I'm giving 0 to HS.
The substrate thickness, which will always start from the 0, and the maximum it will go to the plus z-axis,
Yeah. HS is the substrate height of the substrate. And the material,
which is thickness
which is thickness. Yeah. And the material here they have used is FR4 lossy,
in the
as
front
you can
page.
see.
Zoom it, Harshit.
Yeah. Substrate they have used the material FR4 lossy. So Here, if you want to change any material, we have to go here and we have to we have to select the load from the material library. We can see these prefix and we can search the material here. See, we can see the FR for lossy. We have to select this thing.
And always we have to go for the lossy materials only while designing an antenna.
Yeah. And also you can see the material details here.
And we can check the dielectric constant and everything there.
Yeah. And we have to load the material. Material is loaded. We have to press the
Preview.
preview and we have
And
to give
width
the
of the
dimensions
substrate.
here.
So in the paper, which is already mentioned,
Width of the substrate is 20 mm. So I'm giving here is 20. Enter. And the length they have given is 30 mm. So I'm giving 30 here. And the H is height of the substrate. They have given
thickness
is
is 0.8 mm.
0.8 mm. And we have to press OK. As you can see, the substrate is created here. Now we have to create the ground plane. So for that, uh, yeah,
Yeah, Harshini, keep the working plane.
okay. So for to create the ground plane, we have to follow the same steps as we have followed to the substrate. So we have to select the modeling and we have to go for the brick and we have to click the escape button and the name we are as we are creating the ground plane, we have to give the name as ground or ground plane. So here also I'm giving the variables, not I'm not giving the that constants here. So I'm going with the variables. So same here also minus WG divided by 2 plus WG divided by 2 and minus LG divided by 2 length of the ground and LG divided by 2. So here Z minimum is 0 and Z max is minus HG.
We are going for the minus HG because uh, the ground plane is always placed in the bottom part of the substrate, which should be touched to the substrate. So the substrate itself is starting from the zero, and maximum it is going for the plus z axis, so HS. But the substrate the ground plane has to come bottom of the substrate part, so which will start from the zero and comes in the minus z axis. So we are going for minus HG here.
Yeah. And we have to change the material here. They have given the material for the ground plane is PEC. So here we have to select the same thing. And we can see the option PEC here. We have to
The
select
PEC,
that one, PEC.
which is also called as a perfect electric conductor.
Yeah. And we have to select the preview and we have to mention the dimensions here. So the width of the ground plane is yeah 20.
Highlight that one, Harshni.
Yeah. So width of the ground plane is 20 mm. So and length of the ground plane is 30 mm. So I'm giving 30. And the HG height of the ground plane is
No, it is not mentioned in this paper, Harshni. Every time when we are designing an antenna, always the thickness of the ground plane and the thickness of the patch, which is also called a radiator, is 0.035 millimeters, which is almost it is, in most of the times. This is the common thickness where everyone will use.
yeah. And we have to give the dimensions and we have to click the enter icon or press. Okay. And then we have to select OK here. So here ground has been created. Charan, I guess the length of the ground is 14, Charan.
Yes, yes.
Yeah. See, the length of
Once
the
go to
ground
the
is 14.
once go to the paper.
but they have given the same thing.
No, no, no. We have to follow the table two, Harshni, because in the table two,
Yeah, yeah,
after following the table two dimensions only, we got the better results,
yeah,
like
yeah.
ultra wideband,
Huh. And the
like
length of the
which
ground
is a
is,
which is a partial antenna,
yeah,
partial ground plane.
yeah, okay, okay, okay. See, here I'm changing. Actually, initially I have given the length of the ground plane is 30. I'm changing the ground plane length to 14 mm. Enter F7. So see, it became easy to change the length of the ground plane. If I given the direct constant to the ground plane, it was somewhat tough to change the length of the ground plane.
And
So
we should always remember that in most of the times, whenever we want an ultra wideband antenna, uh, in most of the times the ground plane will be partial ground plane,
yeah,
which is not a fully covered ground plane, which is not fully covered to the substrate.
yeah. So here ground plane has been created, but it was not it was not touching the bottom of the antenna. So we have to adjust the ground plane. So here we have to select the ground plane. Sorry, we have to select the ground plane and Control T. We can see these preface. So here we can give the direct value here, or we can adjust the manually here. First,
Harshni, 1 second.
okay,
Can you make that process somewhat slow?
okay. I'll explain again. See, I want see here the
Harshni, no, 1 second. Remove that grids now.
hmm. Now you can see clearly.
Zoom.
Yeah. So the ground plane has been created. So it has to
Uh,
touch
Once
the
go to the
bottom of,
design now.
yeah. As we can see here, the ground plane is touching the bottom of the substrate. So here we have to adjust the ground plane as it was touching to the bottom of the substrate. So we have to move the ground plane downwards. So we have to select the ground plane here and we have to uh, press the Control plus T for the transform of the selected object. We can see this preface here. So for the moment, we can move this thing manually, or we can give the uh, direct value here. So uh,
If we are aware of the values, like how much distance we have to move the minus y-axis, minus x-axis, or plus x-axis, plus y-axis, we can move in that words if we are aware of the distance. But since we are not much aware how much distance we have to move, so we are going to move it manually.
yeah,
Harshni, move it manually. Or
okay,
1 second, Harshni, you can. There is another simple way to do that. Harshni, once press the cancel now. Cancel
yeah,
this method. Yeah, yeah, Harshni. Now, go for the dimensions. Yes, add distance dimensions.
here we can
Yeah, from
sorry,
that
sorry,
point, uh, uh, and that point.
and we have to select points carefully. So the
So,
distance is 8 mm.
8 millimeters.
So we have to press Escape and then to remove the points. Here we have to press the clear pics here so that the pics will be clear. And then we have to select the ground plane, Control T. We can see these details, and we have meant like we have measured the distance between these two. So we got 8 mm. So we have to the ground plane has to move downwards, right? So it was minus 8 mm. Preview. You can see here. The ground plane has been moved downward. Okay. Charan, I'm proceeding to next step.
Yeah, Harshni, let's go to the design and explain about the slot.
Yeah. Actually, we have created the ground plane like this, and we are designing this design, right? So here we can observe the yeah, we can observe the some gap, like something like gap between
Uh,
the ground plane. That is called slot.
we will call it as a slot. So now we are going to make a slot on the ground plane, and we
Yeah.
can see the dimensions of the slot also. Harshni, show that bottom table.
Yeah. The width of the slot is 2 mm and length of the slot is 3 mm.
But in this paper, that is the only mistake which we have observed. The width of the slot is 3 mm and the length of the slot is 2 mm,
2 mm. Now we are going to
which is mentioned vice versa.
Now we are going to create this slot here. Again, we have to go for the modeling and the same procedure. And we have to press the brick icon and we have to press the escape. And the name I'm giving is slot. Here I'm giving minus WST divided by 2. So width of the slot divided by 2. Control C, Control V. And length of the slot divided by 2. Control C. Control V. As we are creating this slot on the ground plane, so the Z minimum and Z maximum are the same as like ground plane. So for the ground plane, we have mentioned the 0 to minus Hg. For the slot also, it will be 0 to minus Hg. So I'm giving 0 to minus Hg, and the material will be same as the ground plane. Like, and preview. Okay, the width of the slot is 3 mm. Yeah, the width of the slot is 3 mm. We have to select OK. And the length of the slot is 2 mm. Okay. Preview. Okay. So here the slot has been created upside of the ground plane. But if we observe the design of the antenna, the slot has been created just below of the antenna, like here. So the slot is created above the ground plane, but it has to be here. So we have to move the slot somewhat downwards. So
In the previous step, while we are moving the ground plane, we are aware some of the dimensions by checking the distance between 2 points. But here there are no points to check the distance. So we are going for the manual method. Like we will move the slot with the arrows only.
yeah, so we have to select the slot here and then Control T. So here I'm check like I'm moving the slot manually
We have to drag it down.
and make sure that the substrate and the sorry and the ground plane and the slot are in the same.
Yeah, Harshni, once press OK, then you will get then you will be aware of that.
Yeah, see. So we have to remove this slot from the ground
Uh,
plane.
Whenever we want to add the two parts, or we want to subtract one part from the another part, here come the new operations called Boolean operations. So here we want to make some slot on the ground plane. So we are going to delete that slot from the ground plane.
Yeah,
So Harshni, first select the ground plane.
yeah. We have to select the first ground plane and then we have to select the part which we want to remove from the sector.
Harshni, wait here. First we have to select the ground plane. Like we want to create a slot on the ground plane. So first we have to select ground plane. Next, go for the Boolean Harshni. Then select subtract. Yeah. Now select the slot and enter. We can see a slot is created there.
As you can see, the same ground plane here and also here. And then we have created the substrate and the ground plane, and we have created the slot in the ground plane also. And the final part is the patch. So now we are going to design the patch here. So again we have,
Ashni, explain that a patch will be on the front side and everything.
sorry,
Like you have rotated it to the front part, no?
yeah, yeah. Actually, it was back view. For the front view, we have to select the box on box here. So if we click that box, we'll get like different views. So I have to select the front view as the patch is the front part of the antenna. So I have to create the patch here, like in front part of the substrate. So to create the substrate, uh, we have to go for the brick and press escape here. And the name I'm giving is patch. And x minimum is minus WP divided by 2, width of the patch divided by 2. For the x max, WP by 2. And y minimum is minus LP by 2. And y max is LP divided by 2. And the z minimum is here uh, 0, sorry,
Yeah.
HS2,
Ashni,
HS
I
plus.
will, Ashni, one second. So here we can see that uh, Z minimum of the patch is HS and maximum is HS plus H. Harshini, go for the HP, not for HG. Like there will be some confusion in the beginning itself. So yeah. So always the patch will be placed on the substrate. So the substrate is starting from the zero and the maximum of the substrate is HS. So it is extending from 0 to HS up to 0.8 mm.
Charan,
And yeah, Harshini.
sorry for the interrupting, but it will be HS plus HG, Charan. It is not HP.
Harshini, one second, one second. Yeah. It is starting, substrate is always starting from the zero and extending up to the HS. So the radiator, which is also called as the patch, will start from the substrate itself. So the origin point of the patch is not zero. It is starting from the HS above the substrate. So the minimum Z minimum of the patch is always HS, which is height of the substrate, and it is extending up to the HP, like it is the thickness of the patch, which is 0.035 mm. So here we can mention the maximum as HS plus HP or HG because height of the thickness of the ground plane is 0.035 mm and also height of the patch is also 0.035 mm. So in order to avoid the confusion like HS plus HG, we are going for HS plus HP, which is height of the patch. Yeah, Harshni.
And we have to select the preview here. And we have to mention the dimensions of the patch here. And the dimensions of the patch are, you can see the width of the patch is 18 mm. And the length of the patch is 14 mm. Here you can see. And the HP is the same of HG. So the value of the HP is 0.035 mm. And we have to press the enter. And okay, here the patch is created. So we can see this part is created and we have to create the feed line here. So again, I'm going for the break and press the escape button and the name I'm giving is feed line. So the x minimum of feed line is minus WF divided by 2, width of the feed line divided by 2 and WF divided by 2 and here minus LF divided by 2, length of the feed line divided by 2 and LF divided by 2 And the Z minimum I'm giving same as the patch here, as we are going to like as it was creating on the substrate. So Z minimum is HS2 HS plus HP, and the material is same as the patch PEC and preview, and the width of the feed is
two mm
sorry, yeah,
in the first seminar.
width of the feed is 2 mm, and the length of the feed is 15 mm, as you can see here. Yeah, and we have to press OK. And the feed also is created, and we have to adjust accordingly. So, firstly, I'm going to move the feed downwards, feed line
The
downwards.
feed has to touch the bottom of the substrate.
Yeah, we have to select the feed line and Control T, as we can't measure the
Measure
distance
the
between
diamond.
measures the dimension between the feed line and here, because no points are there between the substrate here. So we can't measure, and we don't have any option, and we have to move manually here. So I'm dragging the arrow of the feed line. As we can see, the value is changing here, and we have to zoom and we have to adjust. So it was 7.5. Yeah. So the feed line has adjusted here, and we can check by rotating the angle of the antenna. So for that, we have to press the control and have to drag, like we have to move upwards. So we can zoom here and we can check. Yeah, it is attached. Again, I want front. Yeah. So and also I'm going to move the patch upwards. So for that, I'm selecting the patch and control T. Uh, I don't know how much I have to
We
move.
are not aware of the dimensions, like how much we have to move above or the below. So we are just randomly dragging the elements there.
Yeah. Okay.
Finally, we have to join both of them.
See.
Yeah, you can observe the gap between the patch and the feed line there.
So
So,
we have to read.
uh, in order to add those both elements, in order to perform some addition Boolean expression to the both of them, those two parts has to touch each other. So now we are going to move that patch to the feed line. Like it's the bottom of the patch should touch the upper part of the feed line.
Yeah. For that, we have to select the patch and control T, and then we have to move manually. I have zoomed and like I'm moving. I'm dragging the arrow here. Yeah.
Yeah, it was perfect.
And we have to select OK. So here we have to perform the Boolean expression. So I'm going to add the feed line for the patch. So first we have to select the patch and then shift and like we
Harshini,
can
go for
direct.
Boolean. Harshini, go for Boolean.
Yeah, Charan, 1 minute. We can go to Boolean and we can select the add also here, or else we can directly select the plus icon in our keyboard, select, and we have to select the part which we are going to add. And I'm going to add the feed line to the path, so that I'm selecting the feed line here and enter. So the feed line and patch got added. So we have created this antenna, but we have to create this antenna. The major difference is the slot and the here chamfering of the patch. Slot we have already created here. The only thing we have to do is chamfering of the antenna here. So for the chamfering, for cutting of the edges, chamfering is nothing but the cutting of the edges. So we have to select the edges of the antenna here. For that, we can go to the pick points, sorry, picks, and pick points, edges or face. We can select this one, or we can directly press the yes alphabet in our keyboard so that it will be selected. And we have to select the edge of the antenna. Only line we have to select. So we have to double click here. The edge has been selected, and we have to do the same thing on the other side also. So I'm selecting S here, and then I'm selecting the line only. So the two edges of the patch have been selected. And then we have to do chamfering. For chamfering, we have to go for the blend option here. So if we select the blend option, we can see two options here, blend edges and chamfer edges. We have to select the chamfer edges here.
As
So
of now, according to the design in the paper, we are going for the chamfering part only.
yeah.
So,
So for the chamfering, we'll get the sharp edges. For blend, we'll get the smooth edges. So for the chamfering of the width, we can give direct value or we can give the variable. As of now, I'm giving the variable here. Like I'm giving the CE chamfering edges and preview. So here, as Charan, can I say it manually or according to paper? Can I say?
uh, if we are following the chamfering part in the paper, we are not getting the better results. So, in order to get the better results, we have some other value. So, we are giving that value for the better results.
Yeah. So we have to 6.5 for the chamfering value so that we got the somewhat better results. So I'm giving the same thing here. So 6.5, enter. And you can see the here. You can see the edges here, like chamfering edges. So, okay. The edges has been chamfered and we can see the sharp edges here and here. So, uh,
Uh,
this antenna, this
yeah,
antenna,
the
and
designing part has been completed.
yeah, this
Almost it
antenna
was
will look
completed.
similar. So the remaining part is the only thing we have to create the port. See, the ground plane has been created and the patch has been created. So the only
And
thing left
this,
is port here. So here we have to go for the bottom part of the antenna and we have to select these phase. So we have to go for the picks and I'm selecting the first option. So I'm selecting this phase, double click on that and we have to go for the simulation. As I have mentioned initially, we can give frequency in further steps. So we have to go for the simulation and you can see the frequency icon here. So you have to select the frequency icon and you can give the minimum frequency and maximum frequency here. So minimum frequency I'm giving from 2 to and the maximum frequency I'm giving 11 here and I have to select OK. So the frequency has been given and then for creating the port, we have to go for the waveguide port. So you can see these preface here, and we have to sorry. Before that, we have to calculate some constant value here. For that, we have to go for the home, and we can see VBA macros option here. We can set like if we select, we can see some various options, and we have to go for the solver, and we can see the port icon, and we have to select the calculate port extension coefficient and we have to select for that. So here extension coefficient we have to calculate. So we have to click the calculate here and we got some value here. Just copy that way. And we have to create here, we have to create one variable here, that is K, and to paste the value here, which we copied, and it was created. So for the port, we have to go for the simulation. We have to select the waveguide port and then we will see this preface here. So here we have to give the K into H's. So the same thing we have to give these three. You can see, you can observe the changes in the antenna. And Z minimum is H's. Preview. See, the port has been created. You have to select port. See, the port has been created. Um, So this is the front view. This is the back view. And this is the bottom view. This is the port here. So I'm selecting the front view. And for the simulation, we have to go for the home. And we can select the start simulation here. Yeah, the design of the simulation is completed. We can see the results in the 1D results here, like S11 parameters. So here we have to press the 1D result. We can see the lot of things here, and we have to select the S parameters. So we have to select S11, and we can see the results here. So I'm adding curve markers here. So for adding the curve markers, we have to select the curve markers and add curves. So I'm selecting the points here. So here you can see it is starting from the 2.9 to nearly 10.3. Yeah, yeah. You can see it is starting from 2.9 to 10.3 gigahertz. So it is an ultra wideband we are using. Go to Charan.
Yeah. We can observe the scattering parameters of the design antenna here, which is, as I mentioned in the beginning of the video, which is radiating from 2.94 gigahertz to 10.39 gigahertz, which is an ultra wideband. Uh, these are the final results,
Thank you.
and thank you.